Hello. In the last three lectures, we have discussed various wide area network technologies. There are certain common issues, for example, error control, flow control, congestion control, routing, which are to be performed in all the technologies. And we shall discuss these issues one after the other. The error control we have already discussed, how we can detect error, then we can control error by using suitable ARQ techniques, automatic repeat request techniques. In this lecture, we shall focus on flow control. First, let us try to understand why flow control. Why do we need flow control at all? You have two stations, A, which is performing data communication, data transfer with B. Now, it may so happen that A is a very powerful station, say it is a workstation. On the other hand, B is ordinary personal computer or a PC. Now, the rate at which data can be generated by the workstation is much more than what can be received by the PC. The link can be very fast, say it is optical fiber. But the rate at which the data can be received and processed in station B is less than A. Now, A can send at a very fast rate. On the other hand, B cannot receive at that rate. So, what will happen? The receiver, if it is slow one, it will be overwhelmed. How to protect the slow receiver from a fast sender? That is the basic concept or basic idea behind flow control. So, we have to use flow control so that a slow receiver is not overwhelmed. Let us consider first the basic model, then we shall see how exactly it can be done. The basic model is we are considering just a pair of stations, A and B. So, flow control concerns with only a pair of stations, and this particular protocol is part of the data link layer. So, we have a transmitter which sends data, sends frame, we can say frame, or it can be packet. By this we mean it is sending a portion of data. We have already discussed the disadvantage of message switching. In message switching, a large block of data is sent, and which is not very advantageous. There are many problems in it, and we have seen that. And that's why usually the large or long data is broken down into smaller parts, then it is sent in the form of small frames or packet. And receiver receives in order. That is our basic assumption in this case. You see, here we are concerning between a pair of station. It is not really a network. So since there is a direct link, the order in which the transmitter is sending will be received by the receiver in the same order. Secondly, for the time being, we are assuming that the transmission is error free. So there is no error in transmitting the data. We are receiving data in error free form. Now I was telling about why you have to limit the size of the data, why you have to divide it into smaller blocks before sending it to the receiver. There are several reasons. So let us consider the reasons why data is sent in smaller blocks or which we usually call packet. One reason is limited buffer size. The receiver may have limited buffer size, small size of buffer. So if you send a very long message, there will be overflow. To avoid that, the data has to be sent in smaller sizes. Second is longer transmission time increases probability of error. We have already seen that the probability of error is related to the size of data. As the size of data increases, the probability of error increases. So smaller the size of frame or packet, the probability of getting the frame in correct form is more. And that is one reason why it is preferable to have smaller block size. Moreover, whenever there is error, the frame has to be retransmitted, and if the size of the frame is small, then retransmission time will be small, and so this also helps you to use smaller size of block. Lastly, on a shared media, one should not occupy the medium for a long duration or for extended period. So these are some of the reasons why frames are sent in small sizes, and we have already seen packet switching is popular. Now let us consider, with this background, let us consider the flow control techniques. We shall first consider stop and wait flow control technique. Now, a source entity, we know the active elements in any layer are the entities. Entities can receive data, send data, and process data. So the source entity is responsible for sending data from the transmitter. So the source entity sends a frame and then waits. Waits until receiver receives the frame. Then it requires some time to process the data. It will check whether there is error or not, and so on. And after that, it will send an acknowledgement and send an acknowledgement. It will send an acknowledgement if it is prepared, when it is prepared to receive another data. And the sender, so receiver entity will do this. The source entity will send another data after receiving the acknowledgement. So in this way it continues, and now suppose the destination station wants to stop the flow of data. How it can do that? It can simply withhold sending acknowledgement, and if it's withhold sending acknowledgement, then the sender will not be allowed to send another data. So that is how the flow of data can be stopped, can be cut off by the receiving end. If it is a slow one, it will, until it is ready to receive another data, it will not send acknowledgement, and that's how the flow will be stopped. And this approach will, this procedure works fine for few long messages. But whenever you have large number of small packets, then it does not work very well. And let us see why that is so. Let's assume you have, let us consider two situations. Say this is sender A and receiver B. Let us consider the situation for A is greater than 1 and for A less than 1. Here also you have sender A and receiver B. Now when A is greater than 1, as you know, let me explain what is A once again. I have told it. A is equal to propagation time by transmission time. Let's assume that propagation time is equal to A and transmission time is equal to 1 for simplicity. Now in this particular case, when A is greater than 1, A will send a packet, start transmission at time t is equal to t0, and then after time t0 plus 1, A will send the entire packet which will go in this direction towards B, and then after P is equal to after t0 plus 1 plus A is the propagation time, the packet will be received by B. B receives the packet. Now after time t is equal t0 plus 1 plus 2A, what will be the situation? A will receive the acknowledgement which has been sent by B. So the acknowledgement is received by B. This is 2A. So the entire, for sending one packet, the time required is T0, starting from T0 to 1 plus 2A. Essentially, this is the time required to send complete transmission of one frame. Let us consider another situation where A is less than 1. So at time T0, the transmission starts from A, then at time P0 plus 1, transmission is completed. In this case, say this is A, this is B. A is less than 1, so the packet is quite long compared to the propagation time, and in T0 plus 1, the packet is received, the one end of the packet is received by B. Then at T0 plus 1 plus A, in this time, the entire frame is received by B. B receives the entire frame. And then B sends an acknowledgement at time T0 plus 1 plus A, immediately after receiving the acknowledgement, receiving the packet, and sends the acknowledgement. So at time T0 plus 1 plus 2A, it receives the acknowledgement. So acknowledgement received by A. So this is how it continues. Now if you look at the channel, in this particular case, the utilization is very less. As you see, the packet transmission is starting here, then it is moving in this direction, and at time T0 plus 1 plus 8 is reaching this. So most of the time the channel or the medium is remaining unutilized. On the other hand, in this situation, when A is less than 1, utilization is much more. Now how do you find out the utilization? What is the total time required for transmitting a frame? Let us try to understand. T is equal to T propagation time. We have already discussed it in the context of error detection, error control, plus TF, that is the frame transmission time, plus T processing time, plus T acknowledgement, which is also the propagation time, sending the acknowledgement packet, plus T propagation, plus T another processing when the acknowledgement frame receives the other end. But as we know, these times are small. This processing time, the time needed to send the acknowledgement frame, and this processing time, this leaves with, this is equal to TF plus 2 into T POP. And if you are sending for n frames, the time required is equal to n into T. This is equal to n into TF plus 2 into T propagation time. Now utilization is equal to, what is the total time needed to send n frames? That is equal to n into TF. For each frame will require transmission time of TF. So n into TF is the time required to send n frames. That is the actual time needed for transmission, but total time needed is n into TF plus 2 into T propagation, and this is equal to 1 by 1 plus 2a. So this is the utilization, and as you can see, when the value of a is small, then the utilization is more, as you have seen. In this case, when a is less than 1, utilization is little better. On the other hand, when a is greater than 1 and a is large, which is true in case of satellite communication, and in wide area network, the stations are placed in long distances, they are wide apart, and as a consequence the utilization will be poor when a is equal to large, a is large. How do we overcome this problem? This can be overcome by using a technique known as sliding window protocol. In sliding window protocol, efficiency can be improved by sending multiple frames before receiving acknowledgement. We have already seen the situation for error control. It is somewhat similar, but we shall see how it works whenever there is no error, just it is used for flow control. So frames will be sent continuously one after the other up to some limit, say up to n frames can be sent without receiving acknowledgement. We can explain it with the help of this simple diagram. Suppose these are the frames. It starts with 0, then 1, 2. These are the frames 3, 4, 5, 6, 7. Assuming that you have got 3 bits to represent the sequence number of the frame. We shall discuss it on what basis the sequence number it is decided. But for the time being, let's assume that 3 bits are used to represent the frame number, and after 7 you will again repeat 0, 1, 2, 3 and 4 and so on. This is the source, and in the destination is prepared to receive frames starting with 0, 1, 2, 3, 4, 5, 6, 7, 0, 1 and so on. Now initially both sides sets a window. The maximum, the frames which can be sent by the transmitter, for example, let the frame size be, the window size be 7. So it can send 0, 1, 2, 3, 4, 5, 6. Why we have chosen 7 will be clear very soon. So this is the window. So these are the frames which can be transmitted by the source. On the other hand, the destination has n buffers. In this case, n is equal to 7, which can receive the up to 6. So this is the window size in the receiver. Now window size is same in transmitter as well as receiver. Now it sends frame F0 then frame F1, then F2. After sending these 3 frames, what will be the situation in the transmitter? In the transmitter, what will happen? As the frames are sent, the window size will shrink. After sending F0, F1 and F2, window size will be 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2. So window size will be shrunk from 7 to, it has sent 0, 1, 2. Now this is the window size. After sending 3 frames, initially it was 7, now it has become 4. It can send 4 more frames, 3, 4, 5 and 6. In the receiver, it will receive the frames, now it has sent 0, 1, 2, then 3, 4, 5, 6, 7, 8 and so on. So far it has received up to 2, and once it is received, it also shrinks, the window size also is also shrunk, is reduced. Here also it becomes 3, 4, 5 and 6. It can receive 6 more frames. Now the receiver, after receiving the frames, it will send acknowledgement. Suppose it sends acknowledgement in the form of RR3. This RR3 stands for receive ready frame number 3, which indicates that the receiver has received up to frame number 2, so it acknowledges up to frame number 2, and then it also indicates that it is now ready to receive frame number 3. So that's why it is RR3. Now as the RR3 frame reaches the destination, reaches the source node, source station, what will happen? It will increase the window size. 3 is there, 4, 5, 6, 7, 0, 1, 2. Now what it will do? It will increase the window again by 0, 1, 2 has been received. So 3 more frames it can again send. So from 6 it will go to 7, 0 and 1. Again the window size becomes 7. So here it was 4, now it becomes again 7. On the other hand, in the receiver, after sending this, it will also, this acknowledgement, the window size will be enhanced. Sending an acknowledgement means these 3 packets has already been processed and been sent to the upper layers, and so the buffers of the receiver for 0, 1 and 2 are now free. It can extend the frame, the window size from 3 to 3, 4, 5, 6, 3 more, 7, 0 and 1. So again the window size, here it is 4, again it becomes 7. So this is how it continues. Now we have assumed that the receiver has no data to send, but that is not the situation in practice. As you know, the links are full duplex. The full duplex means both sides can send data. So station A is sending data, station B is also sending data. Now, a small portion of the frame can be used, of the data which is being sent can be used for acknowledgement. This concept is called piggybacking. That means what happens in this case? The receiver is not explicitly sending any acknowledgement frame. Whenever it is sending a data to the other side, say we have got stations A and B. When B is sending a data to, normally say A is the transmitter, and when B is acknowledging, when B is sending data as part of the frame which is used by B, few bits are used to send acknowledgement, and that is called piggybacking. And so no separate acknowledgement is necessary, acknowledgement frame is necessary. However, when station B has no data to send, then an acknowledgement frame has to be sent. Another point is multiple frames can be acknowledged. What can be done? Say this is your transmitter. It has sent F4, F5 and F6. Now the receiver can send an acknowledgement RR7. It means that the receiver has received all the previous frames up to 6 without any problem. So it acknowledges up to frame number 6, and it is now ready to receive frame number 7. This is how 3 frames have been acknowledged by sending a single acknowledgement frame, and that can be done by piggybacking. Whenever you are sending data, the receiver has some data to send. Now suppose the receiver station does not want to receive data because of some reason or the other. Its buffer is full, or it is not able to process the data, whatever may be the reason. The receiver is now unable to accept more data. So how the flow can be cut off or stopped? That can be done by using receive not ready RNR frames. For example, instead of RR7, if it sends RNR7, it means that the receiver has received up to frame number 6, but it is not ready to accept frame number 7. So the transmitter should not send frame number 7 right now. So this is how the piggybacking can be used. Multiple frames can be acknowledged by a single frame, and also when the receiver wants, it can send a received not ready frame to stop the flow of frame. Let us now consider the performance. The performance of sliding window flow control depends on two parameters, n, the window size, and a, the ratio between propagation time by transmission time. Now, this window size n depends on the number of bits that is being used to represent the frame number. Let's assume 3 bits are used. With 3 bits, you can have 8 possible numbers, 0, 1, 2, up to 7, using modulo 8 arithmetic. That means using modulo 8, it will go up to from 0 to 7, then it will repeat 0, 1, 2, up to 7, and so on. With 3 bits, when the number of frames is 8, the window size has to be taken equal to the power n minus 1, where n is the number of bits. That means 1 less than the maximum number of sequence numbers. That is necessary because we have discussed while discussing the error control technique, so that the retransmitted frame and the earlier frame number do not coincide, do not match. This is necessary. Now, the value of n with 3 bits is equal to n is equal to 3, then capital N is equal to 7. That is the window size. If you take n is equal to 7, then small n is equal to 7, then capital N will be 127. That means 128 minus 1. On the other hand, the propagation time, the parameter A, depends on the ratio of the propagation time by transmission time. And it depends on the speed, the distance between the two systems, because the electromagnetic signal travels at the speed of 3 into 10 to the power 8 meters per second through unguided media, and roughly 2 into 10 to the power 8 meters per second through unguided media. It also depends on the transmission time, and with the increased speed of the data transfer, as you know, in high speed LAN and wide area network technology, the transmission time is getting reduced, and as a consequence the parameter A is becoming higher and higher. Let us consider two cases. Case 1, where the window size n is greater than 2a plus 1. In such a situation, let's assume this is your transmitter and here you have got your receiver, two stations A and B. Now in time A, there will be A frames because the transmission time has been assumed to be equal to 1 and propagation time has been assumed to be equal to A. With these assumptions, you will have 1 to A frames simultaneously on transit, 2, 3, 4, in this way up to A on transit simultaneously. Similarly, after the end of A frames, the receiver will receive the first frame and it will start sending an acknowledgement frame which will start propagating in the reverse direction. And by the time 2A frames are sent, that means here it will be A plus 1 and here it is 2A. Then the acknowledgement frame will reach the station, that means the transmitter. And by that time, this is your acknowledgement frame has reached. Now, since in this case n is greater than 2a plus 1, the transmitter has some frame yet to be sent before this acknowledgement is reached. So the number of the frames to be sent to the window does not get exhausted in this situation, and it will have a continuous flow of frames one after the other, just like a pipeline. As the water flows continuously, this in a similar way you will have a continuous flow. On the other hand, in case 2, when n is equal to less than 2a plus 1, what will happen? Before this acknowledgement reaches the transmitter, the acknowledgement sent by the receiver reaches the transmitter, the window size will get exhausted. So a portion of the transmission path will remain unutilized, because during this period, during this time, nothing can be sent by the transmitter, because the window size has already got exhausted and window cannot be expanded until the acknowledgement is received. So in this situation, you will not have continuous flow, and the values of utilization. Let us see how the utilization changes. The utilization U for phase 1, where your n is greater than 2a plus 1, utilization is equal to 1. As I said, you will get a continuous flow. On the other hand, for case 2, n is less than 2a plus 1, and utilization can be expressed as n by 2a plus 1. If we plot the parameter a in the x-axis and utilization in the y-axis, we shall get the curve for different values of window as it is shown here. For n is equal to 1, which is equivalent to stop and wait, the utilization is always less than 1, and as the parameter a, value of parameter a increases, the utilization decreases, as you can see. On the other hand, when n is equal to 7, that means you have used 3 bits, then utilization is 100% for up to a is equal to 3, and then of course it decreases as the value of a increases. Up to a is equal to 3, utilization is 100%. For n is equal to 127, that means for a is equal to 63, 63 into 2 plus 1 is 127. So up to a is equal to 63, utilization is 100%, that means utilization is 1, and then it decreases as the value of a increases. Now you may be asking, why not have the window size longer? Unfortunately, that cannot be done because the overhead of the frame will increase. The number of bits that is used to represent the frame number is used as part of the frame. So the number of bits will increase and overhead will increase if the window size is longer. Normally, for LAN applications, n is equal to 7 is adequate. On the other hand, when you are communicating through wide area network over a longer distance, then n is equal to 127 has been found to be very satisfactory. When you are communicating through satellite and over a long distance, then n is equal to 127 is sufficient. Now, in this lecture, we have discussed the flow control technique by which a slow receiver is protected from being overwhelmed by a fast transmitter. And in most of the wide area network technologies that we have discussed, the X.25, the frame relay and ATM, this flow control is used to some extent, degree varies, from technology to technology, but it is being used. And in the next lecture, we shall discuss other aspects like congestion control and the routing techniques. Thank you.